Let me tackle the second module for building construction, structural form, and structural efficiency. Introduction. The performance of a structural element is determined by its shape and by the properties of the constituent materials. This chapter explores the relationship between form and performance, and especially the effect of structural geometry on the efficiency with which particular levels of strength and rigidity can be achieved. The shapes of the structural elements, especially the shapes of their longitudinal axis in relation to the pattern of applied load, determine the types of internal force which occurs in elements and influence the magnitudes of this force. These two factors, the type and magnitude of the internal force created by a given application of load, have a marked effect on the level of structural efficiency which can be achieved. The effect of form on internal force type. Elements in architectural structures are normally subjected to axial internal force, to bending type internal force, or to a combination of these. The distinction is an important one insofar as efficiency is concerned, because an axial internal force can be resisted more efficiently than a bending type internal force. The principal reason for this is that the distribution of stress which occurs within axially loaded elements is almost constant, and this uniform level of stress allows all of the materials in the elements to be stressed to its limit. That is to a level which is slightly lower than the failure stress of the material. An efficient use of material therefore results because of the material present provide full value for its weight. With the bending stress, this varies in intensity in all cross sections. Only the most highly stressed part of each cross section are used efficiently. The effect of cross-sectional shape of the efficiency with which bending type load is resisted. A good example is to get a thin card which has an efficient rectangular cross section. Thin card folded to give an efficient improved cross section. So the effect of cross-sectional shape on the efficiency of elements which carry bending type loads. A rectangular cross-section, high bending stress occurs at the extreme fibers only. Most of the materials carries a low stress and is therefore inefficiently used. An improved cross-section efficiency is increased by elimination of most of the under-stressed material adjacent to the center of the cross section. The efficiency of a non-form active element can be improved if its longitudinal profile is adjusted to conform to the bending moment diagram, so that high strength is provided only where the internal force is high. Example, a solid beam is less strong and rigid than a triangulated structure of equivalent weight. So let us consider here a sample problem. Given a combination of simple cantilevered beam carried by a fixed and roller type column. So here we need to solve for the shear moment diagram. Show solution by presenting the free body diagram and joints. So take note that the 4 meters from the strut or column extended 4 meters till it reaches denomination A. The height from the roller is 4 meters. And then the simply supported beam here has a span of 15 meters. So at the end of the other side of the structure still has the same cantilever length, which is actually 4 meters. So here we made use of a free body diagram to compute the loading. So take note that this is 3 kilonewton times 4. That is why we were able to obtain 12 kilonewton, which is found at the center of the beam, which is actually divided into 2 parts, meaning there are 2 meters on each side of its span. Then 3 kilonewton meter times 15. That's why we will do attain 45 kilonewton. Then just divide 15 meters. We were able to obtain here 7.5 span. So same process as we have done on the other side, just transfer it here. So this is already your free body diagram, or abbreviated as FBD. Now to present it clearly, so each section of this cantilever beam, take note it is 4 meters. It was in a exploded view. That is why we were able to subdivide it into its different parts. So this is already the layout of the each structural members. So take note that joint B is at this portion. That is why we denoted it as joint B, which is found here. And this joint C, that's why if we're going to look at the designation of it, it is in this manner. All you need to do is just transfer the loadings to the joint. In that way, you'll be able to transfer the shear and moment diagrams to it. So here, because this one is a cantilever beam, you could see that the shear stress is actually manifested at this area. So for the shear diagram, take note, this is negative 12. That is why here, all you need to do here is just transfer the load to this point, because the downward force is actually pointing at this direction. So the neutral line is actually found at this side. So therefore, so take note, because of the moment diagram here, so the loading here is the 12 kilonewton, and the derivation of the moment diagram, we're able to obtain here 24 kilonewton, and the negative will represent the direction of your moment diagram, which is actually found below the neutral line. So all in all, if you're going to present it in this manner, so the shear diagram is actually pointing to this joint, and your 34.5 kilonewton. If you're going to subtract this, it becomes 22.5 kilonewton. But take note, the force that is actually exerted here will also be the force that carries this beam. That is why the strut or the column is actually carrying the beam. Now, we were able to attain 45 kilonewton because if you're going to multiply 3 kilonewton over meters, just multiply 15 kilonewton. In that way, the sign or the unit of meters is actually eliminated. Then if you're going to look at it, because 22.50 kilonewton is already being transferred to this direction, it is actually pointing upward. And eventually, if you're going to look at this, the sign convention again is negative 22.5. That is why we need to transfer the value here, which is actually negative. In that way, we are able to solve already the shear diagram of this simply supported beam, which is actually negative 22.5. So it is very important that we should also consider here as the symbol for it. So take note, this is decreasing positive, then gradually it is increasing negative. That's why if you're going to look at the very center of this, because this one is decreasing negative, decreasing positive, so naturally the curve will follow this line. Then eventually it is actually increasing but negative, so eventually this will be the line that it will follow. So this is now what we call the first degree line. Eventually, because it is a first degree line, the next line will become already a curvilinear line. So take note, this is decreasing positive. That's why here your line convention later on would be manifested in this manner. So you need to solve for the following: solve for the reaction, solve for the shear diagrams, and solve for the moment diagram. So step 1, to solve for the reaction of RE. So we are actually referring to this reaction. So RE is the reaction under strut E. So when you say RD, this is the reaction at strut D. That is why here we have denoted it as, for step 1, reaction under strut E. So the summation moment of D is equivalent to 0. So all moment arms are at clockwise direction. It is presumed to be negative. And all moment arms at clockwise direction is presumed to be positive. So here, the reaction of E is 15 meters. So meaning, if it is in a, so take note of our presumption, the moment arm at clockwise direction is presumed to be negative, and moment at which is actually presumed to be counterclockwise is positive. So therefore, reaction of E is 15 meters. So as you can see here, reaction of E, then just get here the meters. So it is positive. Then the next convention here is 12 kilonewton times 2 meters. It is positive. So meaning same direction, you have 12 kilonewton times 2 meters is positive. Then you have negative convention times the distance is 7.5. So here from 45 kilonewton till it reaches this direction, which is actually 7.5, is presumed to be negative. And then your 12 kilonewton that has a span of 17 meters is negative. So meaning because this is 15 meters plus 2 meters, it became 17 meters when it reaches this point. That is why the presumption here is negative kilonewton, which is 0. So now the reaction here, if we're going to take the summation of all forces at D, we're able to derive 34.5 kilonewton. That's why here you could see that the reaction in R's of E, we have 34.5 kilonewton, which is this. Okay. Or step 2, so for the reaction of D, so summation moment at E is 0. So all arms at clockwise direction is presumed to be positive, and all moments arms at counterclockwise is presumed to be negative. So same process as we have conducted in our R's of E. So RD is 15 meters. So meaning from here, R's of D, the moment arm reaches to point E. So R's of D is 15 meters. It is presumed to be positive. And then negative 12 kilonewton because it is counterclockwise times 17 meters. So meaning from this direction, your R's of the D is actually benching at this mark. So 12 kilonewton, we have here 7.5 plus 7.5 plus 2 is equivalent to 17 meters. So it is presumed to be negative. Now 45 kilonewton times 7.5, we have negative here. So if we're going to look at the diagram once again as our reference point, so take note, this is 45 kilonewton times 7.5, but because it is in a counterclockwise direction, it is presumed to be negative. That's why here you were able to come up with this sign convention. Now you have 12 kilonewton times 2 meters. So if you're going to look at the diagram once again, so here you have 12 kilonewton, then it is in a clockwise direction. That is why it is presumed to be positive times 2 meters. That is why here under step 2 we have a sign convention which is actually positive. Now R's of D have the same value as R's of P, which is 34.5 kilonewton. So to check if all forces vertical is in equilibrium, so all you need to do is come up with a summation of all forces vertical is equal to, or in equilibrium, all forces upward direction is equal to all forces acting on downward direction. So therefore, 12 kilonewton plus 45 kilonewton plus 12 kilonewton is equivalent to Rs of E plus Rs of D, which is actually equivalent to 69 kilonewton. So all forces acting upward and downward forces are in equilibrium. So meaning they are in a balanced state as indicated in this diagram. So it is very important that we need to understand how we're able to arrive to the reaction Rs of D and Rs of E. So meaning all forces that is actually pointed downward, you need to add all of this and add the reaction of D and E, which is actually compensated by the summation forces acting upward and downward, which is actually in step 3, which is equivalent to 69 kilonewton. Now for step 4, at member AB, which is actually cantilevered beam, solve the shear and moment diagram and the joint at B. So for step 1, the shear diagram for cantilever beam summation forces vertical is 0. Downward direction is negative force. So for step 2, take note that we're going to look at the step 1 under this diagram. This is actually 0, okay, for the shear diagram. Because if you're going to look at this, at A, there's no force being carried because it is found at the point or at the tip of the cantilever beam. So there's no support. Now, let us continue the moment diagram for the cantilever beam. Because summation moment at A, there's no force being exerted, it is also 0. That's why if you're going to look at it, at A, everything is found at the neutral axis, which is actually at 0 axis. Now, let us take a look at the so under step 4 at member AB, which is actually the cantilever beam. So now let us look at how we're able to solve for the summation moment at B, which is negative 24. So there is actually a moment arm. So 1/2 times 12 kilonewton times 4 meter. Because this one is found downward, it is negative 24 kilonewton meter. So let us take a look at the diagram here. So take note, there is the half of 4 meters, 2 meters. That is why 4 divided by 2 is 2 times negative 12 kilonewton. So here 3 kilonewton times 4 is 12. Then 12, we have a moment arm which is actually 2. That is why we were able to attain negative 24, because this one is pointing downward, or it is in a clockwise direction and downward direction. That is why we have negative 24 kilonewton. So all forces acting on it, so meaning it is found downward. So all you need to do here is just transfer your moment at this side. Now at joint B, solve for the shear at joint B. Summation forces vertical, all upward forces is positive and all downward directions negative. So VB2 equals to negative 12 kilonewton plus 34 kilonewton. That is why we have 22.5 kilonewton as what we have presented it here on the joint B. So all you need to do here is negative 12 kilonewton add 34 kilonewton. That is why we were able to attain 22.5 kilonewton. So just transfer this at this direction because it is actually pointing upward. So from the neutral axis, this is 0. Then measure it. It becomes 22.5 kilonewton, which is actually pointing upward. Now, to get the total loading, so meaning you need to subtract 34.5 kilonewton, which is actually positive, minus 45 kilonewton. So if we're going to divide the loading here, simply it will be able to carry this load already. So take note, R sub B is the reaction which we already have solved it. So all you need to do here is just put it to this free body diagram. Now let us see how negative 22.5 kilonewton was actually solved. So let me under number 2, solve for the shear diagram, which is actually VC1. So take note, under VC1 is 22.5 kilonewton minus 15 meters times we have 3 kilonewton per meter, which is actually equivalent to 45 kilonewton. So therefore, 22.5 kilonewton minus 45 kilonewton, we're able to get negative 22.5 kilonewton. Forces is downward direction. This is the reason why we were able to attain this value. Negative 22.5 kilonewton. So meaning if this is decreasing positive, so this line is known to be your first degree. So meaning it already becomes a second degree, so in the shape of a curve already. This is increasing negative, so at the tip we have this one is first degree, so therefore the second degree is a curvilinear line. So this is how to interpret the shear diagram to its moment diagram. So now for the simply supported beam under step 5. So this is already the last portion of the cantilevered structure of the figure. So you need to solve the shear and moment diagram at members B and C. So solve the shear diagram under VB2. So we have VB2 minus 12 kilonewton plus 34.5 kilonewton. We have VB2 is 22.5 kilonewton. Forces is upward direction. So this is it, the 22.5 direction. So now let us compare the other side. So for V, C1, so we have 22.5 times 15 times 3. So here we were able to solve for VC1, which is negative 22.5 kilonewton. So we have a downward direction, which is negative 22.5. So this is already the negative 22.5 direction. As you could see here, negative 22.5 meters. So here, this is negative 22.5 plus 34.5. We have 12 kilonewton. It is pointing upward. So therefore, the shear diagram is found or located upward. If you're going to compare the cantilever beam here and at this point, they are in a reverse process. Then take note that because this is decreasing positive, the curve this is first degree. So meaning the line here becomes second degree or curvilinear line. So this is how important to interpret the solution once presented in a shear diagram. So you need to see how it is actually correlated to your moment diagram. So now solve for the median of simply supported beam. So by ratio and proportion, so we have 45 kilonewton divided by 15 meters equals to 22.5 kilonewton times x. So therefore, the distance is 7.5 meter, which is actually we are referring to this. You're able to solve for the median of this triangle ratio and proportion. So meaning you need to come up here the ratio of 45 kilonewton times 15 meters. Then here we have a ratio of 22.5. Just presume this one to be x. Then you can already solve how much is the value, which is actually 7.5. So now this is the solution, how we are able to arrive to this ratio. So take note, 45 kilonewton is actually a right triangle, then 15 meters, then eventually by ratio and proportion 22.5, just presume the distance to be x. So this is how to determine the distance of 7.5. So meaning just presume this to be x. So because at the tip, so here if you're going to look at it from 45 kilonewton, so we have 15 meters span, because take note 7.5 plus 7.55 is 15 meters. Then eventually here this is another right triangle, you have 22.5, then just put here the value of x. So therefore you are able to solve for the median, which is actually 7.5. Now solve for the moment diagram. Formula for moment diagram is equivalent to W times L raised to 2 divided by 8. So here the load is 3 kilonewton times 15 meters, because this formula is for a simply supported beam. We were able to solve for 84.375 kilonewton meter. Okay, so I already have shown here how it was derived. So for solve for the maximum moment, under negative 24 kilonewton meter time. So add 1/2 22.5 kilonewton times 7.5. So here, because this is negative, just subtract it. Maximum moment therefore is 60.375 kilonewton meter. So this is 60.375 kilonewton meter. So solve for the maximum moment at the cantilever and simply supported beam at moment C. So we have 60.375 kilonewton meter minus 1/2 of 22.5 kilonewton times 7.5. Moment at C is negative 24 kilonewton meter. So this is the derivation of your negative 24 kilonewton meter. At joint C, you need to solve for joint C. So the summation forces vertical, all upward forces is positive and downward is negative. So VC2 is negative 22.5 kilonewton plus 34.5 kilonewton is equivalent to, so therefore VC2 is 12 kilonewton positive. So this is already your positive 12 kilonewton meter. So take note, this is a cantilever beam, so the shear is pointing upward to counteract this load coming down. For step 7, so at member CF for the cantilever beam, you need to solve for the shear diagram. So summation forces vertical is 0. All upward forces is positive and all downward forces is negative. Now, we were able to attain this, which is actually 12 kilonewton. So just transfer this to this side. So take note that because you have positive 12 kilonewton minus 12 kilonewton, VF therefore is 0. That's why here, if you're going to look at the diagram, so this is VF, so because this one is positive and this is negative, therefore F is 0. That's why if it is also 0, meaning your moment here is also understood to be 0. So this is how important to indicate all loads that are possible even if it is 0. Okay, so solve for the moment at F. Are we able to arrive at moment of F is equivalent to 0? So take note, MF is negative 24 kilonewton plus 1/2, 12 times 4 meter. So we have negative 24 plus 24 is equivalent to 0. So this is how the solution is explained why we were able to attain at 0 moment. Now if we're going to complete the figure, this is the complete figure of what we had solved for the cantilever beam and simply supported beam. So we need to translate the beam with the help of the free body diagram, afterwards the shear diagram, then the moment diagram. So this is how important diagrams are to interpret the structural integrity of our structural members. This ends the lesson.